This is video 15 in the series on concrete slabs. This video deals with the design of slabs against punching. Punching is a ULS failure mode, and when you have a column or a point-like support, on top of it a slab, then you can have a crack developing like that and forms a critical failure cone. When the slab is loaded by uniform distributed load, the slab will come down when those cracks are too extensive. So punching is in fact a two-dimensional shear force mechanism. You see here an example after the failure of the slab. You see here that the punching cone rests on top of the column. When you look at the top, you see here the circumference of the failure cone, and internally you can see the cracks developing at failure. Also a picture of the damage that can occur by punching shear. The reinforcement for punching shear, there are different models for it or different methods. The most common method is this shaped stirrup. You can also have other stirrups, combined stirrups, and you put the reinforcement within the first critical failure surface. You can also have punching shear reinforcement like this, but the most commonly used or most practical used are the dowels, the punching shear dowels mentioned here or on this next slide. You see that those dowels are very easily put down and with no big effort. The different mechanisms of the critical punching cone. Suppose that the distance LH is smaller than 2 times the depth of the first part of the concrete. If this is the case, there is no cone that can be developed like that, but the first punching cone will be like this. It means that the depth is the effective depth d, and the horizontal distance is 2d. So, and this is the slope of the expected punching cone. When LH is equal to 2 times the depth of the first layer, then of course you only have one punching cone, which is like this one. When LH is bigger than 2 times H and LH is smaller than 2 times D plus H, and the sum of those two, then you will see that you have again 2 punching cones where the horizontal distance is 2d and the vertical d. Here the horizontal distance is 2 times d plus h and the vertical is d plus h. Again, this is the same, but now the punching shear cones are separated from each other. VED is the design value of the imposed shear stress in the control section. And VRDC is the design value of the punching shear resistance of a slab without punching shear reinforcement. And VRDCS is the design value of the punching shear resistance of a slab with punching shear reinforcement. And VRD max is the maximum value of the maximum punching shear resistance. Step 1, we start with the calculation of VRD max, is the maximum punching shear resistance. Step 2, we define the first, second, and so on control parameter. Then we calculate the design value of the imposed shear stress alongside this control parameter. Then we calculate the design value of the punching shear resistance of the concrete. Then we will decide if there is punching shear reinforcement needed, yes or no. If yes, then we will calculate the punching shear resistance of a slab with the punching shear reinforcement, and we will check the outermost control parameter, and after that we take care of the detailing of the reinforcement. So we have 8 steps to reinforce against punching. We start at step 1, which is determine the maximum punching shear resistance. The shear resistance is given by a coefficient beta times the shear force or the reaction force of the column divided by the circumference of the first critical perimeter divided by the effective depth d. And this must be smaller than the maximum allowable shear stress, punching shear resistance. The VRD max is equals to half of nu FCD, and nu is the coefficient given by this formula, and mu0 is the perimeter of the edge of the column, Beta is the coefficient depending on the situation depending on the location where the column is situated, and it's also a function of the bending moment and the shear force at that point. The W1 is then given by, it's a geometrical factor, and it's given by geometrical conditions, where C1 and C2 are the sizes of the column, the first one parallel with the eccentricity, and the other one is the size of the column perpendicular with the eccentricity. And the factor K depends on the proportion C1 to C2, and a linear interpolation is possible. FCD is alpha cc times FCK divided by gamma c, but for punching, alpha cc is 1. Then we have to check the control parameter, or to calculate the control parameter, mu0, and mu0 is the column circumference. So when it's a central column, then you see that if it's one side C2, the other one C1, it's just the circumference of the central column. When we deal with an edge column, then it is the size of the column parallel to the edge is C2 plus 3 times the effective depth, and this must be smaller than C2 plus 2 times C1. So smaller than the circumference of the column. And when it's a corner column, then it is 3 times the effective depth of the slab plus C1, and it should be smaller or equal to the circumference of the column in contact with the slab. So we have this step 1, the maximum punching shear resistance. We have seen what is VRD max. When you have an internal column, this factor beta, and for a circular cross-section, because this was done for a rectangular cross-section, but for a circular cross-section, the formula can be rewritten as beta is equal to this formula. And for a rectangular cross-section, where you have 2 eccentricities, when there are a bending moment in 2 different directions on top of the column, it's an eccentric load, then beta can be written in, can be calculated with this formula. In practice, we will use a slightly simplified beta factor, and for a middle column we use beta 1.15, an edge column we will use beta 1.4, and a corner column we will use beta 1.5. If you want to make more precise calculations, or if the eccentricity VED of the column reaction is large, is significant, then of course you should use this general formula as stated here. As an example, we will calculate beta for a central column, and a central column subjected to a bending moment and a vertical force. The column is 300 by 300 millimeters, and the effective depth of the slab is 160 millimeters. The support reaction is 180 kilonewtons with a bending moment of 20 kilonewton meter. The critical perimeter, the first critical perimeter, is equal to the circumference of a circle with a radius of 2d, which is this portion, plus 4 times the straight lines of 300 millimeters, so the circumference mu1 is 3211 millimeters. The proportion C1 is 300 divided by C2, 300 is 1. It means from the table that K is 0.6. The W1 factor, if when applying the formula with C1, C2 and D, then we had 1 million square millimeters. And the factor beta is then 1 plus the K value, 0.6, plus the bending moment divided by the reaction force, it's the eccentricity, times the mu1 times the length of the critical circumference divided by W1. And we arrive at 1.21. So if you compare that with the standard value of 1.15, then you will see that the 1.15 is increased due to the eccentricity of the reaction force, because you have a bending moment and a vertical load, a vertical reaction. Step 2, we will calculate the control parameter. The first control parameter is at 2D, the second control parameter is at 4D, and so on, 6D, 8D, and so on. The first control parameter, we calculate what is the effective depth, the mean effective depth regarding the tension reinforcement, that's D. Then we take a distance 2D from the face of the column, and then that's our critical parameter. This dotted line is the critical parameter for a circle shaped a cross section of column. It's obvious, and it's just the circle circumference with a radius of 2d. For a rectangular, we have a quarter of a circle with radius 2d 4 times, and then the straight portions on both sides. A more complicated column shape, always the same principle. You take a distance of 2d and you draw the lines at the distance of 2d. There you have the quarter of a circle, here too, distance of 2d, you stop there, distance of 2d, and then you take the tangent line, and then you arrive at that. So this is the critical circumference at a distance of 2d. This is for an edge column, this is also for an edge column, and this is for a corner column. It's obvious. Step 3, we calculate the design value of the imposed shear stress. It's in fact the same formulas as we've seen just now. It is beta times the reaction force divided by the surface, and the surface is the first or the second or the third critical punching circumference, and divided by the effective mean depth d. Step 4, we calculate the design value of the punching shear resistance. This is the resistance given by the concrete, and this resistance is given by this formula. and it must always be bigger than a minimum value. K1 sigma Cp is when there is a constant normal stress in the cross-section. It means, for instance, that this is the case for pre-stressing slabs. Then you will have this constant factor sigma Cp times the value K1. In this formula, it's like the same formula as for shear force. CRDC is equal to 0.18 divided by the material factor of concrete. This is the mean reinforcement ratio. This is the ratio in the x direction and the ratio in the y direction. And you should take as D always the mean depth of the two layers of reinforcement. The first layer in x direction, the other layer in y direction. And it consists only of the tension reinforcement. Factor K is a dimensional factor. It's given by this formula. It must always be smaller than 2. And K1 is 10%. And the minimum value for the shear force is given by this formula. Then step 5. Is there punching shear reinforcement needed? Yes or no? We only can find out by comparing the acting shear force with the resistance shear force given by the concrete alone. If this is the case, then there is no punching shear reinforcement needed. If this is not the case, then you need punching shear reinforcement. The punching shear resistance of a slab with punching shear reinforcement is given in step 6, and it's given by this formula. You will notice immediately that there is a component only a component proportional to the resistance of the concrete only, and there's a component which is given by the punching shear reinforcement. This is an important difference with shear force in beams. Then this component will be 0 for beams. The alpha, the angle alpha, is the angle of the shear reinforcement to the vertical. It's the angle of the shear reinforcement, but in most cases we will take alpha equal to 1. It means that this straight or vertical shear reinforcement. You can rewrite this equation for directly calculating the needed shear reinforcement. This formula here, it's only valid for sinus alpha equals 1, but because this is now 1, then in general there is a minimum shear reinforcement required, which is the minimum shear reinforcement divided by the distance radial in the radial sense and the distance tangential, and then again depending on the angle of the reinforcement, and it must always be bigger than the value square root of the concrete quality divided by the steel quality, and then 8% of it. Most of the times sinus alpha is 1 or alpha is 90 degrees, so this equation will be like that. Now we must take care the maximum stress in the punching shear reinforcement is limited. So this is limited not to the yield strength, but it's limited lower than that. It's limited to 250 plus d over 4 and must always be smaller than the yield strength. So this value here, FAWVD, which is the yield strength of the punching reinforcement, but taking care of this limit. Then when you have a plan view, this is the column. Then this is the first perimeter of the critical punching shear in a zone of 1.5D. In this zone, this is the reinforcement area. where you put the reinforcement for the shear. And if you take a cross section, then you will see this is the first critical circumference and a distance 2d and a distance d. Then all reinforcement must be situated within a zone of 1.5d. The total resistance for shear force is the resistance of the concrete plus the resistance of the reinforcement, which means that you can only count on 75% of the resistance of the concrete because the concrete is cracked at the punching shear, and then the resistance of the reinforcement is given by VRDS. VRDS, it's simple, it's in fact just the cross sections of the reinforcement times the yield stress, and then of course times the sinus of the angle that the shear reinforcement is placed. The total shear reinforcement is the reinforcement ASW per perimeter. You can have different perimeters of shear reinforcement, and ASW is the shear reinforcement per perimeter, and then the number of perimeters is of course given by the total width that is allowed, which is 1.5d, divided of course by the radial distance of the two perimeters reinforcement. So this is the number of perimeters, and this is the reinforcement per perimeter, gives you the total reinforcement, and this gives you then the total resistance. If you can just now convert this in stresses, so you will divide that by the circumference times by the depth of the slab, then you arrive at this formula. You can simplify this formula, and then you will see that we have the formula as mentioned earlier. Step 7 is a check. We are looking for the outermost control parameter. This is the parameter where the shear stress from punching is equal to the resistance shear stress of the concrete alone. So VED must be equal to VRDC. It means outside this parameter you will not need additional punching reinforcement. And this VED is written as beta, and then the reaction force VED divided by the circumference mu times the effective depth. And if you substitute those two, then you see that mu out, of course, is the outermost parameter due to the force VED times the coefficient beta, depending on if it's middle column, edge of corner column, and then divided by VRDC times D, because it is the parameter where the shear force is equal to the shear force given by concrete alone. This outermost parameter has a function, and this function is that the last parameter where reinforcement is put, the last parameter, must be within a zone of k times effective depth, and k is 1.5. So within the zone of 1.5d of the outermost control parameter, there must be the last parameter of reinforcement. And you have always at least 2 parameters of reinforcement. Then step 8, the detailing of the reinforcement. You see here the critical, or you see here the cone, the punching cone. Then you will see that the first parameter of reinforcement must lie between 0.3 and 0.5 times the depth of the slab. And the distance between two different parameters of punching reinforcement must be smaller than 0.75 times D. And then you see that if B here is the outermost critical of outermost parameter, then you will see that within 1.5 D of this parameter, your last reinforcement parameter must be situated. You can also place the shear reinforcement in a rectangular or in a grid. In a grid, then you have the same kind of reasoning. You can summarize it by, let's say that this is the outermost control parameter. Outside this, you don't need reinforcement, punching reinforcement. Inside, you will need punching reinforcement. The last parameter of reinforcement, you take here this dotted line, must be within 1.5 D. The distance between two reinforcement parameters must be smaller than 0.75 D. The first parameter must be between 0.3 and 0.5 D within this limit. And then SR, the radial distance between two parameters, it's SR. And then ST is this distance, and the tangential distance between the punching reinforcement. So you have a lot of parameters to place or to design the punching shear reinforcement. There are many solutions to one problem. There are many different solutions. This gives you also another view, but maybe more. It's a summary of the different rules. That is the outer control parameter within 1.5 times D. The last reinforcement parameter is there. The first one is between 0.3 and 0.5 D, and the distance between is 0.75 D. And you will always have at least two parameters of reinforcement.